Let's talk about the Rocket Lab. I'm just going to take, you have actually 4 sets of data, and maybe you did 4 trials of each thrust washer. I'm just going to take one example. So this is what I did for the high, and you'll have to do this for all 4 of them. Okay. I think it's a reasonable thing to take the average. Okay, these all should be the same, and so I'm going to average these guys, right? So I'm going to go 6.21. 6.21 plus 6.31 plus 6.42 plus 5.98 and divide by 4. Except I've got to actually type them in correctly. Okay, here we go. Let's see. I'm sort of excited by this. Let's see. 6.23. Okay. So I get 6.23 as my average. Comes out nice and even, coincidentally, right? The next thing I think is reasonable to do is understand that, that rocket, when we launched it off, right? Okay, the rocket went pow up in the air, right? And we reacted to that. It went bang, and then sometime later we pressed stop on the stopwatch, and then when it came down, we could see it coming down. So we were actually fairly accurate at that. So I think that the time that we have on our stopwatch is actually short. So we need to add the reaction time. So let's suppose I know that it takes me on the average about 0.21 seconds. And if you don't know, you could just say, well, it's about 0.2. I've done this with the Physics G kids. What we do is we drop a ruler and we see how far it falls. I've also seen IB kids do it with like 2 stopwatches to estimate the reaction time of their timer. They start them in unison, and then one person presses the stop button, the other person reacts to that. That's reasonable. You tend to get that people react at about 0.2 seconds if they're expecting it to happen. And it's as simple as pressing a stopwatch button. So what I'm going to do is I'm going to add 0.21. Okay, so, and I just made this up. So let's suppose you know that it's 0.21. So 0.21. And I get 6.44 is what we think it really was in the air for. Okay. The second thing we also need to do is we actually need to figure out the uncertainty of it. Of time, right? Okay. If you have multiple trials like this, the uncertainty, okay, is just the range divided by 2, okay? So our range is, let's see, the highest one is this guy, 6.42, minus the lowest, 5.98, over 2. So parentheses 6.42 minus 5.98 divided by 2. And that's 0.22. Right? So this is, the uncertainty is that it's plus or minus 0.22 seconds. Okay? So we've got the time, we've got the uncertainty of the time, right? We want to make a nice data table for this, right, with the units and everything labeled, etc., etc. Okay, so let's see how good a job we can do with this. Every single trial will have a different uncertainty, like that, a different range divided by 2, and so you'll have to have a column for the uncertainty of time. Okay, now the next thing we got to do is we got to figure out what the initial velocity is, right? And so what we do is there's 2 more calculations, right? The uncertainty of the velocity and the velocity, right? So let's first calculate what the velocity is, right? And that's easy. We're just going to Suvat this, right? The initial velocity is what we want to find. The final at the top is 0. The acceleration is negative 9.81. And then, of course, if we know our free fall problems, we know it reaches the top at half the time, right? So the time, this is key, right? The time is half the time here. So we got 6.44. So we think it got to the top at 3.22 seconds. Half the total time. Okay. And now we're all set. We can find the initial velocity. 3.22 times 9.81. Basically, it's just that times 9.81, right? If you want a formula, the formula I'm using is V is U plus AT, right? So 0 equals U plus negative 9.81. That's supposed to be a U. Okay, times 3.22, right? Okay. And the answer I'm getting is 31.5882. So I'm going to say it's 31.59. Just for fun. Meters per second. Okay, so that's my velocity, right? And now I want to do the uncertainty of the velocity, right? Well, you know, what is my real formula? Basically, my formula is that the initial velocity is 1/2 g times t, right? Basically, I'm taking the time, dividing it by 2, multiplying by 9.81, and not negative 9.81, right? And so therefore, the uncertainty of the initial velocity is to the initial velocity. And then 1/2 doesn't count because it's exactly a half, right? It would be the uncertainty of gravity over gravity plus the uncertainty of time. Now, I'm really hoping that this looks familiar because we've, I don't know, done 10 of these or something like that. Okay. Now, I'm going to propose that the uncertainty of gravity is negligible, right? Because it's 9.81, it's like a constant. It's like the uncertainty of pi, only somewhat more uncertain, right? So I'm just going to cross that off, and now it just becomes a direct proportion, right? So I can just set this up, right? The uncertainty of the initial velocity is to what we think it is. That's this guy here, 31.59. And that equals the uncertainty of the time, 0.22. Over the total time, which we think is 6.44. Although one could argue maybe we'd use this, you know. I'll have to think about that. Okay, so anyway, I'm going to take this number here, right, multiply by 0.22, divide by 6.44, and I get about 1.1 meter per second. Okay. And now we look at this thing, right, and it's like 31.59 plus or minus 1.1. I think 2 sig figs for a derived uncertainty is good. I think what I would say is it's 31.6 plus or minus 1.1. That feels the best to me. Ta-da. Such a lot of work, and you have to do this 4 times. Okay? So step 1, find the average. Step 2, add what you think is the uncertainty. If you don't measure the uncertainty, you could probably safely add 0.2. Okay, but if you're feeling industrious, especially if you're an IB student, and you're going to be submitting this for, you know, you should have some basis for your reaction time, right? Then to find the uncertainty of time, right? That's this thing, right? So step 1, step 2, step 3, find the uncertainty here, right? Step 4, calculate what the velocity is. Step 5, calculate the uncertainty of the velocity. Yay.